Folks, lesson 5.3, adding and subtracting polynomials. This is all about combining what we call like terms. So it's important to be able to add them, subtract terms, and solve a few problems that we throw your way. By like terms, we need to get at that right now and say what it is exactly we mean by that. So at this point, when we introduce terms to you, like terms are similar values. So I'll throw a couple examples down here. It always helps. You could have y to the second power. You could have, in the mix, we could put the number 35. We could have an x understood to be the first power, and maybe even an x y beastie. And I like to use a zoo analogy. These are all very different animals. The y to the second power term, or the y squared term, is very unique. The number 35 is a constant. X to the first is some variable. And xy, that's a totally different beast. So when we look at a zoo analogy, you have to look at what the value is and look at it as a base and say, well, is it unique? Is it like the other things that are there? Before you go combining like terms. Because as a zookeeper, I don't think you want to put the wrong animals together in the basically in the same cage. You wouldn't want to do that. So like terms are values. So let's do a little bit of writing here. I need a little more space. Say combining like terms is a process. So the bases have to have similar exponents. Together. So when we look at a y to the second power, well, its base is y, and its exponent is to the power of 2. The x is to the power of 1, and for x, y, the base is an x to the first, y to the first. So they're very different terms. So when we go to put variables with similar exponents together, that's one thing. When we look at the number 35 there, that's a constant. Well, you can combine constant values with other constant values. So if we had 35 and in came in 2 more, we'd say, well, we have 35 plus 2, or 37. You'll see examples of this as we go along. But let's finish our little bit of writing here. Just want to make that point about constants with constants. There we go. So there's a great number of examples. If I leave half for you and do half, that'll give you a chance to try a few of these, take it out for a spin. Now, when I look at the values inside the parentheses, they can't be combined. An x squared can't be combined with an x to the first. Not until we really know what x is. So on to the left of that, I see there's a 3x squared decreasing by 2 times x. Right now, I'm just going to drop the brackets because nothing can go on inside anyways. I've filled everything that I could do. 3x squared minus 2x combined with an x to the second power and add x to the first. So what do we got? Using the highlighter, I can see that I've got an x squared term there and another one there. So that's good for 4 x squared terms. So what we're doing is we're adding how many it is that we're talking about. There's an understood 1 in front of that x squared term, so there's 4 of them in total. And lastly, we say, well, what do we have for x terms? We've got -2 on the left, and we have 1 on the right. So -2 plus 1, that's like -1. Not bad. Let's go to a slightly different color. Go back to shocking purple. This is 7r minus 8 plus 3r squareds, or yeah, 3r squareds, minus 11. Now this sign here just says combine this stuff on the right as it is with the stuff that's on the left. So make a real careful point of noticing that doesn't change anything. Plus signs don't go reversing signs, and that's going to be really important for you to know, because in the examples that are going to follow, that's not going to be a plus sign. That's going to be a decrease or a minus sign, and it will have an effect on the items in the parentheses to the immediate right. Now when we look at this, we have a 3r squared term here, so I'll just use a little room to the right here. 3r squared, and it's positive. Now that 7r, you might wonder, well, what do I do with it? Well, it's got positive value, so if you don't know what to write down, think about what the value of the sign is. 7 is positive, okay, plus 7r. And then lastly, we've got minus 8 combined with minus 11, which is good for minus 19. I have to push this out of the way. There we go. And that works. In our example below, you're starting to see the approach to this. Once you know how to do this, if you notice that's a plus sign, you can sort of skip, I guess I call it half a step, and find similar terms. So since this is a positive value, I'll just leave these ones in here unaltered. 7t squared minus 2t is good for 5t squared. So remember, we're looking at t squared terms. Next, is it done? Let's choose this. Next, we look at the t terms. Well, interestingly enough, it's like there's 6 dead ones on the left and 6 live ones on the right. Minus 6 and positive 6, they cancel out. There's no t's left. So since there's none, we just don't write it. But we do have 9 being decreased by 5. Let's make sure that's obvious. That was a 5t squared. And this, last little bit, 9 minus 5 is 4. So 5t squared minus 4. As part of the course, what they do expect you to be able to do is to understand the opposite of the values you're going to be working with. Right now, you're working with what we call polynomials, or many terms. And we look at positive values and negative values. So this is going to get a little tricky with black and white when you're just writing on paper, or you're using, say, handouts. But what we're going to try and do is anything with color we're going to treat as positive, even if it's darkened in. And an absence, right? An absence of filling in any color or anything, we'll just treat as negative. So white will be negative, and anything colorized or dark will be positive. It's important to note that these little squares are constant squares. And by constant, we know their value. So these little ones over here are worth 1, and these ones are minus 1. This represents a value, let's call the variable x. Okay, so that's a positive x tile, and this is a negative x tile. Tricky what they do here. They have x by x, so they refer to this as an x squared. So I'm just going to squiggle these out now that I don't need them. So this is a negative x squared. Okay, so you have to take that in and say, all right, I see what you're doing. The little squares are just counting numbers, positive and negative. The rectangles represent variables, say to the first power, and the squares literally are squares, like x squareds or y squareds or however you decide you're going to use these. Following a pattern like that, can you figure out what the expressions are below? If you're watching the video, hit pause and see if you can figure it out. Okay? I'm going to obviously proceed with my answering of it right now. What I see down here is I see an x there and an x there, and each of these is good for minus 1. So in total, if I was playing Zookeeper, this would have, there's 2 x's there, and there's minus 1, minus 2, minus 3. There's 3 of those negatives. So the expression is 2x minus 3. Looking at this, I know that this is a negative x squared, and that these, just alternate here, are all minus x to the first values using our scheme. So this expression would be negative x squared minus, or decreased by, 3 of these x's. When we look at opposites, what defines an opposite? It's opposite in terms of its sign. Let's make a note of that. So they're either opposite, as in positive, or negative. And below, what they'll do is they'll get you to look at a few of these and say, hey, what's the opposite sign? So the opposite of the opposite of 6a, where the coefficient is 6, would be minus 6 of a. Can you apply that to c? It's positive d squared, there's a minus 8d, and there's a positive 2. Notice how I looked at each of these. I thought about whether they were positive or negative before I decided to go after the opposite. So the opposite of a positive d squared is a negative d squared. The opposite of a minus 8d is a plus 8d. And the opposite of a plus sign is a minus sign. There you go. So your expression is its negative opposite. And if you look at these, you will see that it follows the same pattern. Negative 3 for the coefficient becomes positive 3c squared, and that minus becomes a plus 9. Negative 6w squared minus 4w. Right, keep your eyes on these because these are going to take a little turn. So those are opposite versions of the expressions. And some of my students will look at this and they'll say, well, what's w? For now, think of it as we're working with formulas and we're gathering like terms. We're getting these nice, concise formulas. We're working our way closer towards algebra. And in order to be good at algebra, you really want to be good with formulas and expressions and gathering terms, because some of the greatest equations in history, such as E equals mc squared, Einstein's theory of relativity, started out as a multi-board monstrosity until lots of combining of like terms was done, and we managed to figure out exactly what it was down to this highly refined little formula. That being E equals mc squared. In example 4, they're checking to see if you are on the ball and you see that there's a minus sign here. Because what it will do, that minus sign, literally means the negative of. And negative of, it means the negative of everything that follows. Oh, okay, so that's why I was showing you this, previously showing you opposites. Because this is 5a minus 4, but this negative sign affects everything after it in the parentheses. So this becomes a minus 3a plus 2. Now you can go to collect like terms right now. You could see that if you hadn't done that step, you would have had positive 3a minus 2, like what you originally saw in the brackets, and you would have got a completely erroneous collecting of like terms. It'd just be wrong. What we have now is 2a minus 2. Now, for space reasons, I'll come over here and point out this negative sign here has a downstream effect on all the signs. So this is 7 minus 6r decreased by 3 minus r. When you go to combine your terms, be careful and see what the values are. Look in front of the r. Is that a plus 6 or a minus 6? It really does matter. Switch up colors here. Needs a little change. We have negative 7 r's and 7 decreased by 3 is positive 4. So I write in exactly what it is. As far as r's go, it's minus 7 of them. And as far as constants go, we have 4 of them. In this case, it's positive 4, so we write plus 4. Do a couple more examples here. Oops. Again, the negative of affects these that follow. H minus 1. This fellow was positive. Now he's not. When you go to write it, you can write things in any order as long as the sign is correct. Now, when I look at this, when I go to collect my terms, I don't see another h squared there. So let's change the color, just because I don't want you to miss this, and say, look, as far as h squared go, there are negative 3 h squareds. Take that off now since we've written it. I've written it with the minus sign in front. That is its true value. This h here, all alone, has nobody to combine with, but it is positive in value, so we say plus h, and the constants combine to give us negative 8 in value. So we go like that. Nice and neatly arranged. So in these examples, it's very important to pay attention that when you're combining polynomials and there's a minus sign, you sort of have to say, halt the presses. What does that do to everything after? It changes the signs. It makes them all opposite. It's pretty important. It's something you don't want to miss. It'll wreck a lot of work, let's put it that way, if you've been working on a problem and that's something you forgot, and you look at your answers in the back of the book and you're like, shoot, what did I miss? Oh, it didn't apply that negative. once they get you combining polynomials and getting it down to a nice simple formula, then they'll throw things at you. They might look at a triangle perimeter. So perimeter of a triangle would be like as if you took a trip around the outside. Well, same thing with quadrilateral. If you drove from one town to another, from there to there, from there to there, and let's say round trip like that. Now, in an example like this, they say this is a scalene triangle, and they're expressing the sides in a different way. It's just a comparison. You can see the longest side on the bottom, and they're saying, well, the comparison of these sides are kind of relative to x. If we knew what x was, this would be a cinch, but we don't. So if this is how long the sides are, what would the expression be for a trip around the outside? Well, everything about this lesson has been combining or subtracting or whichever your polynomials. This will be no different. So a trip around the outside of a triangle requires that you add up all the sides. So the unsimplified expression, I don't think I want to use red. Let's go to a darker color. Unsimplified expression for the perimeter. Perimeter is just the addition of all the sides. Unsimplified means write it like you see it. So the one side is x plus 2. The next side is 3x minus 9. And the next side is 2x minus 6. I like to write it like this because it really shows what things I'm combining. Those larger size plus signs aren't there to throw you. I just want you to know which side was which. If x is equal to 6, go ahead and figure out your work. Well, in an unsimplified expression, I haven't gathered any terms. You can sort of see what's coming. If this is a 6, and that's 3 times 6, and that's 2 times 6, we've got a lot of work to do because we've got 6 minus 2 plus 3 times 6 minus 9, and the third side, which you have to add on, is 2 times 6 minus 6. Okay, this is getting to be a lot of work. There's got to be a simpler way. There's a lot of junk here. So when you crank out your final answer, you probably could have done it on just this one line, this first line. I had it there. 6 minus 2 is 4, plus 9 plus 6. Okay, so we've got, the answer is 19. So that's the perimeter if it turned out that x was 6. Like I said, there's got to be a simpler way. This is taking too long. Easy way is get your formulas figured out. Tidy it up. If we go back and we say there's got to be a way to simplify this, we had x minus 2 plus 3x minus 9 plus 2x minus 6. There we go, about like that. How many x's do we have? Like, let's get this down to the bare bones of what the formula really is. Well, I can see that we have 1 there, 3 there, and 2 there. So if you combine their coefficients, you've got a total of 6x, and the constants, that's minus 11, right? And that's minus 17. So another way of saying the perimeter of that triangle, if you add up all the sides, this would be your expression. Now remember when they said x is equal to 6? Let's check this. If this expression is so all that, it should totally work out. Let's check it. 6 multiplied by, turned out They said x was equal to 6 back up here. 6 times 6 minus 17. If this is right, we should get the same as that. 36 minus 17, perfect, 19. So if this expression is the exact same, this expression, the one I'm talking about right now, the simplified one, is the same as the unsimplified one. It's just a lot less work, and that's what you got to realize. Famous, really famous formulas that we're familiar with, like E equals mc squared, Einstein's theory of relativity, relating matter and energy. Well, how do you think it got down to E equals mc squared? A whole bunch of combining of like terms, canceling. It was it think of it as filling multiple boards before it was refined down to such a simple little formula, E equals mc squared. That takes us to the end of 5.3. So I'm going to hurry up and post this one. A few people that wanted to look at this and take advantage of it. So folks, have a good one, and we're done.